Okay, Assalamualaikum warahmatullahi wabarakatuh. Okay, for today I will discuss a new topic. Okay, titled Exposed to Risk. Okay, this slide is Exposed to Risk Part 1. Okay, this topic include in the CT4 course, where this topic be the hardest part for most of the students. Alright, so it is impossible to memorize, all answers because of the various combination, but mainly because it appears so illogical. Right, but if you all understand the concept of exposed to risk or how to calculate the exposure, I think all of you will find this topic very interesting. Okay, so we recap back some points about exposed to risk that we have been that have been covered in previous chapters on the different models available to us. Okay, so if you see here, it would seem logical to only have one measure of exposure, which is uniform across all models and investigations. Okay, in practice, there are two basic problems that must be addressed. First is the Poisson and multiple state models are based on the assumption that the force of mortality is constant over the year of age. Okay, however, we know this is incorrect. So the study will often use external data, the external data collected from the pool experience of the various life insurance company. In this case, the data may not be classified according to age exactly as desired. Okay, so we must group the data according to the age level. Labels appropriate to the form of the available data. Age level means age nearest birthday or age next birthday and age last birthday. Right? So then we estimate the mortality rate. It is important to determine what age is implied by the chosen age level. So the data may be incomplete, or we call it or we have the missing data. So we have seen how exposed to risk arises in probabilistic models of mortality. So for example, the MLE. Okay, in maximum likelihood estimations. So in the particular, we have the central exposed to risk denoted by EXC. Okay, this was the total observed waiting time in the Poisson and multiple state models. Second one is the initial exposed to risk denoted by EX. Okay, this was used in the actual estimate of QX in the binomial models. So given by the approximations, your initial exposed to risk equals to central exposed to risk plus half times by numbers of deaths between HX and HX plus 1. Okay, this only apply if we don't have accurate data. If we have individual data recorded, we should be as accurate as possible. So now we consider some problems of computational nature, concerning the approximations of the exposed to risk from the incomplete data. Okay, the central exposed to risk, or we call it as waiting time, is natural quantity. Okay, observable, even observation may be incomplete. So we are simply required to record the time spent under the observation for each life. So the initials exposed to risk require an adjustment respect of each life observed to die. Okay, the initial exposed to risk is more difficult to calculate, okay, compared to the central exposed to risk. So apart from the idealized binomial models, which end life are observed for the entire year of age without sensory, the interpretation of the initial exposed to risk is less intuitive. Okay, what is censoring? So censoring means if a study is continued until predetermined numbers of death has been observed, right? So the center exposed to risk can be readily extended to more complicated multiple decrement and multiple state models. However, this is not the case for initial exposed to risk. Okay, when the observed data is incomplete or we have missing data, the central exposed to risk can usually be ready approximated, whereas the calculation of the initial exposed to risk require further assumption that can be difficult to justify. Right, so this is if you have missing data. Okay, so previously actually tend to use binomial models to develop the live tables. So the quantities required were rates of mortality QX, which are easy to interpret and communicate. So communicate with the non-actuaries to understand, which they understand the QX is the value of the probability that someone age X will die in the next year, or a person age X will die between age X to age X plus 1. Okay, calculation of initial exposed to risk was required, but in practice, the binomial model was also extended to allow the multiple decrement. Okay, in this case, it became increasingly difficult to interpret exposed to risk in terms of underlying process being modeled, as life can't count towards the initial exposed to risk if they have moved into a different state. Okay, move to different state from healthy to unhealthy. Okay. Examples. Okay, compare with the simplicity of the central exposed to risk in either Poisson or multiple state framework, much of the difficulty can be avoided. So if possible, a Poisson or multiple state approach should be used. Even when the binomial model is used, we will often need to calculate the central exposed to risk and then adjust. Now is the heterogeneity. Okay. The multiple state Poisson models and analysis are based on the assumption that the observed groups of identical life, or we call it as homogeneous, where the mortality characteristics are the same. So underlying all model we have considered in is the assumption that we observe a group identical life. Okay, group of identical life. So in practice, they will not be possible. Okay, it's not possible. So to reduce heterogeneity, we can divide the data according to characteristic known from the past, taken from the past experience to have significant effect on the mortality. Among of the factors in respect of which life insurance mortality statistics are often subdivided to sex or gender, according to age, type of policy, okay, smoker and non-smoker, level of underwriting. So level of underwriting is for some types of policy of insurance, life are required to undergo a medical examinations, and also the durations, okay, of the policy. Other possible factors could be included is occupation, okay, high risk workers, or you work in the high risk environments. Okay, so geographical locations, for example, if you stay policyholder or insured stay in the urban area or suburban, rural, or even they also want to know whether you stay in the high or low risk area. Okay, so for the size of policy, example level of sum assured, how much of your policy sum assured. So if sufficient data were available, then the Cox regression model can be used. Okay, but you must take note that Cox regression model itself does not model the mortality, but instead adjusts only the baseline hazard function of another models. Right, so subdivisions cannot be carried out unless the relevant information is collected. Okay, some factors for which there is a strong evidence effect on the mortality cannot be used because the data is not recorded on the proposal form. For example, proposal form are often kept as short as possible for the marketing and administrative reason. So subdivision using many factors will result in a much smaller population in each class. So in practice, a balance must be struck between reducing homogeneity and reduce the credibility of the analysis. Okay, for the principle, okay, this is the principles of correspondence. So we are now in the position to actually start considering the problems that can be caused by life being labeled in different way. Okay, so mortality investigation based on the estimation of QX or mu x plus half. We want to estimate the QX. All right, at individual age, require two different items of data. Okay, when you want to estimate QX, okay, you estimate QX, you need to know the numbers of death in the observation, divide by the total exposure. Right, it is crucial that this item should be defined consistently with regard to age, or resulting ratios are meaningless. Okay, these data are often obtained from different sources within the life office. For example, death data you obtain from the claim file, while your exposure data you obtain from the premium collections files. Okay, so there is no guarantee that the same definition of age will be used, or when we are doing an industry-wide investigation, we may find that different companies use different age definitions. So the principle of correspondence require a life alive at any time t should be included in the exposure at age x. All right, so the central exposed to risk if and only if where the life to die immediately, it would be counted in the death data at age x. So death number of death between age x to age x plus 1. Example, when we're calculating the crude estimates of mortality, we must ensure that the definition of age used in the numerator, the x is the same as definition s used in the denominator, the total exposure. Okay, so when you calculate the estimate of your qx, okay, make sure your total number of death, all right, divide by the total exposure, use the same age definitions. Okay, we have specified the age of policyholder as a last age birthday, and the principle of correspondence hold triviality. Example, we have view age as we do in a normal life. So other definition of age are often used. Okay, it is vital to ensure that the principle of correspondence still holds. Okay, so this is how the exact calculation of exposed to risk. Okay, so for each life of age x, the contributions to the central exposed to risk, okay, is simply the period span under the observation. So the observation, for example, this timeline, this is your, okay, first start of the observation is 1st January 2012. Then end of the observation 31st 12 2018. Okay, this is start of your observation. Okay, this end of observation. Right. So it is different between the start date and the end date, where the start date is the latest of the date of reaching age X. For example, the date of reaching age 31. Okay, the start date of the investigation period. Okay, and the date of the entry to the observation. So the second one is the end date is the earliest of. Okay, the end date. Okay, the date of reaching age X plus 1. Right? So, you know, because why X plus 1? Because we estimate the QX between X to X plus 1. Right? Estimate interval. So, the end date of the investigation period, okay, and the date of exit from the observation. Date of exit the observation for any reason. So reason of death because of death or withdrawal, or other than death, we call it withdrawal. Right? Okay, in other words, what we are saying is that for the life to contribute to the exposed to risk, it must have the correct age and still be observed in the part of the investigation. Must fall in the observation period. All right. Then the center exposed to risk take account of all movement in and out. Okay, of the population rather than just death. So for example, withdrawal and its independence of the cause of exit under considerations. Most of the time, data on the exact date of entry to and exit from the observation may not be available. Right? Okay, so just now we discussed about the exact calculation of exposed to risk. Okay, now the census approximations to the central exposed to risk. Okay, it is often convenient for a company to record the total number of policy in force on the date such as 1st January every year. Okay, so instead of the data exact date of entry to and exit from the observation of the for the each life, suppose that we only have the following census data for PXT. PXT is the numbers of life under observation each X last birthday at time T, where T is the 1st January in the calendar year, K plus 1 until K plus N plus 1. Okay, the observation period cover the complete calendar years, so N plus 1. Okay, so from the start calendar year K to the end of the calendar year K plus N. So complete year means you consider 1st January 2012 until 31st December 2012. This is complete of 1 year, calendar year, complete of calendar year. Yes. And if then you can do for 1st January, the observation from 1st January to 2012 to 31st 12 2020. Okay, so note that although we are only observe PXT, the discrete time, the value will be changing constantly between these observation. This is one source of confusion among the students. Okay, it seems to think that the value of PXT only happen at the time it is observed. Suppose all dx, okay, dx is numbers of death between age x to age x plus 1, is the total number of death age x last birthday during the observation period comprising the n plus 1 complete calendar years, k plus 1 until k plus n. Note that we do not need the precise timing of this death. So you don't need the date of death or date of withdrawal. Okay, no need, right? So the center exposed to risk over the observations period is given by EXC equals to integrate from K to K plus N plus 1 PXT dt. Okay, so however, the problem is that we do not know the value of PXT for all T, only the observation or census date. So we must estimate the value of central exposed to risk given the available census data. Okay, the simple approximation, we use the trapezium assumptions. Okay, trapezium assumption. Okay, so example, assume that PXT is a linear function between the census. Okay, so if we draw the trapezium assumption, okay, we denote this is A, B, C, and D. Right, so A to C is the numbers of policy in force at the start of year. So PXT. Okay, so this is A to C. So B to D is the numbers of policy in force at the end of year. Okay, PXT plus 1, complete calendar year. So the base is C to D. Okay, C to D. So period, this is period between census, right? Data. Okay, C to D. So period between the census data, if 1 year, then times by 1 lah, the base. This is the base. Okay. This is the base. So now the base is 1 year lah, 2015, 2016, 2016, 2017. So 1 year. Okay, so formulas of areas for trapezium. Okay, so equals to half. Okay, A, C plus B, D times by C, D. Okay, trapezium. Okay, so this is formula. This is you will learn in your SPM. So the central exposed to risk is equals to, you integrate from K plus till K plus N plus 1 PXT dt, or approximate to half PXK K plus PSK plus 1. Okay, times by 1 lah, base the 1 lah, 1 year. Okay, half, then plus with half times by PX K plus 1 plus PX K plus 2 times by 1 year, the base. Okay, until so we can summarize that the central exposed to risk approximate to summations of T plus K until K plus N, right? Time, half times by PXK plus PXK plus 1 times by the base. Okay, 1 year lah. Right? Note that as we all our assumption, if they are not true, then our estimate is a false estimate. Okay, in practice, this is the form that the life insurance data are submitted to the CMIB. Okay, CMIB is the Continuous Mortality Investigation Body, and the above approximation is often used to calculate the central exposed to risk. Okay, the method can be easily adapted to allow the census data available at more or less frequent interval or even at irregular intervals. All right. Okay, I end my discussion on the exposed to risk part 1, and I will see you guys on the next discussion, exposed to risk part 2. Right? Thank you.